A question on, technically it's last week's work at this point.
Yeah,
We're comparing the objects, between the two classes.
yeah.
How did you expect us to do that? Because I got so frustrated, I think that was great now. And they have all of this stuff that like it's just a variable.
Yeah, yeah, you should be extending the parable, and I can make it share too.
So you can want that.
Yeah. Yep,
If it was not mentioned anywhere.
correct.
Sitting there like.
I like to do this occasionally. I will happily tell people if they come to me with what should be done here. But when it's an implementation of something from a prior class, I like to build that intuition of, is this the right place to use this? How do I do the part that's not? I'm the exact opposite of trying to make you do it in exactly the way. I like opening the door and saying, implement it the way that makes sense to you, or the way that you've seen before, and if you don't know, reach out and ask, and I'll happily get you started on the right path.
Yeah, this is from a higher class, just say that my
Yes.
having any classes here is fairly.
Yes, and I can certainly understand. Yeah, we go over comparable and comparators very. We gotta beat it to death in 211, of course, before this.
I don't think. Like 1, 2, 3. Yeah. I saw you, I got your sister, sound.
No, it's space.
All right, we should get started. I feel like we should start with some announcements because this week is important. Lots going on this week.
What is this?
So now that we're through the AQ, we don't have to structure everything exactly to maximize the overlap between the 8th and the course, which is nice. So we have the 2 assignments that are due on Wednesday. And today is that deadline for getting extra feedback on it before Friday, because Friday is going to be our next exam. There is a study guide up on Canvas for you to peruse. So at some point, getting into assignments this week, studying for an exam, we'll have our review session for that the day before. So this Thursday, there will be no new content. I will just be answering questions and helping you to prepare. The last section on that study guide is material we have not yet covered. So over the next couple of days, we are going to be covering that content. But do note that it did say the kinds of questions will be limited to conceptual questions on stacks, and there will be no implementation. So we should be mostly through that. Today is my goal. And as you have questions on that, feel free to ask me during office hours over email, or bring it up during the review session. And there should be enough time to at least have a conceptual understanding of this concept. Questions or concerns about where we are or what's happening this week within the scope of this class? I do want to talk to people about their experience with the APE, especially with how it relates to how I could improve the first half of this course to better help people prepare for the APE. I don't really want to prepare people for exact questions, but if there's anything that this course can do to help you to learn to or start to think the way that you need to be successful on the APE, that's what I really want to get out of the first half of this class. So now that you've been through that and been through the APE, I would love to hear your feedback on that so that I can help the next batch of students that I have in this class. Although I was originally scheduled to teach this class once next year, but now I think it's been pushed to the year after. So who knows how soon I will implement that, but I'd still like to hear the feedback regardless. Anything else before we dive back into a quick recap of recurrence relations before we move past it? We are going to do that. So we talked about recurrence relations. The purpose of them was to figure out the runtime order or runtime complexity of a recursive function. Our example with factorial was, we said T of n is going to be the time that it takes for this function to run when the input is n. Since for factorial, that's going to be the n that is passed into the recursive function. We said that the complexity of t of n is the complexity of t of n minus 1. So we're going to solve the problem with for size n minus 1. But it's going to be constant to put that back together. It's constant time to break it apart and put it back together. After that, we just have to figure out the complexity of what is it like to solve a problem with size n minus 1. So we broke it down. We also said the base case, the time it takes to return that 1 factorial is 1 is also constant. So we can just start to break it apart. To actually do that, no, this is for Fibonacci. We didn't really, I don't draw it out here on the slide, but you can see that t of n equals t of n minus 1 plus 1. You would continue to break that apart into t of n minus 2, t of n minus 3, t of n minus 4. And at the very end, there'd be a bunch of 1s, and the number of 1s there would be n of them. So that's how we know that factorial was linear. It was much more difficult to find a recurrence relation for Fibonacci because we had to break it down, and there ended up being multiple different instances of particular values. So you can see in the very last row here, back substituting, we end up with t of n minus 4 and t of n minus 5 a bunch of times. So to calculate this all out, it ends up being exponential in that the terms grows exponentially, especially as we get down toward those base cases. Something like t of 1. So when we saw a difference between the iterative version of Fibonacci and the factorial version of Fibonacci, after we started calculating 40 something, a depth of 40 something, the iterative still finished instantly, but the recursive version ended up taking a couple seconds to come to an answer. So even though it's like so long in practice, that would just continue to grow exponentially as we got deeper and deeper into the recurrence. So everything past this is just the implementation that we already did. We implemented binary search and we implemented Hanoi. We didn't really analyze the complexity, or did we? I think we ended doing that last class, the last class we had. So we said that t of n was based on t of n over 2. If we're doing some kind of binary search, then we're solving that problem with proportion to a problem that is half the size. So that's why we have t of n on the left and is a function of t of n over 2, because we can construct the complexity of a problem of size n based on the complexity of a problem of size n over 2. But it looked like something like n over 2 plus 1, which said that it's one extra step put together a solution for n if we have a solution for n over 2. And that led to a logarithmic complexity, because just like we've seen a bunch of other times, everything that's logarithmic, one axis gets a plus 1, one axis gets a times 2, or a divided by 2. So when we get that relationship by using a recurrence relation that has t of n on the left, t of n over 2 on the right, and a plus 1, because you can also have recurrence relations that are something like t of n over 2 plus n, or t of n over 2 plus something else that's not just 1, and that will also change the entire order of the recurrence relation. So you can't just look at the variables on the left and the variables on the right and know the answer. Oftentimes you do need to break it apart and put it back together in order to figure out what that is. But because there's a plus 1 here, it did turn out to be logarithmic. So I think that's basically the extent to which I want to go into recurrence relations. It is a full unit in algorithms, the course after this on the same vein, so CSCD 320. You will be going into the master method, different ways of analyzing or shortcutting some of this work to do recurrence relations. The reason I bring it up in this class is to get you an intuitive idea of what it is, why we use it, and that way when it's brought up much more mathematically and proof-based in algorithms, hopefully you have something intuitive to grab onto. So remember this topic, it's not really gonna show up too much more in this class, aside from trying to figure out the running times of a couple other recursive sorts that we will do. But this is basically everything for sorting. We are gonna dive right into the next thing. Questions before we do this? Anything I can draw out, explain in more detail? Or do we feel like we're good to go? Feels like a Monday to me too. I see it. I see the defeat on everyone's faces. I shouldn't be laughing. That is, I feel that too. I'm right there with you. That's what I mean. So let's look at a stack structure. Who's heard of or is familiar with a stack and knows what it is and what it's used for? A few people.
No, for Magic the Gathering.
Yeah, right. If you play Magic and resolve spells in Magic the Gathering, that does utilize a stack. And it is exactly the same structure. So we've done a lot. Both the prior classes and this class have talked a lot about lists. But lists have a big downside in practice. There is no list implementation that gives us both constant time get and remove. You can kind of have one or the other, depending on your implementation of a linked list. You can get remove reasonably quick. But we need a get and a remove that are both constant, or we want some way of being able to do that. The question from this, so I guess we can first dive into, we know that array lists have a fast get method. We know that linked lists have a fairly fast remove method. But now what we are interested in doing is placing additional restrictions on a list structure so that what is the minimum amount of functionality that we have to lose to be able to get a constant time get and remove? That's the question that we are going to be answering. So think about this for a second. We want a constant time get and remove, but neither of these structures can do it. Is there a place where we could do this? Is there, given these implementations, what would we need to do? What functionality would we need to say, all right, we can't do this, but this is the functionality that is restricting the constant time get and remove? Any ideas about what that might be?
Both of those are dependent on trying to find something. So
Mhm.
restrict get removed to one location that you can always access to.
Yeah, that's a very good insight. Yeah,
So like the tail of the list.
yeah, so if we wanted to only get and remove from one place in the list rather than all over the list, and that one place can't really be in the middle because then we have to manipulate other things that are around it. So thinking about what happens if we're at one end of the list or the other end of the list. So we're always adding and removing at either the head or the tail. Now, based on the implementation, that's going to change the associated complexity. So an array list has a really slow remove when we're removing from the head, but a really fast remove when we're removing from the tail. So yeah, what if we restricted this to just the tail? What would that look like from a list's perspective? That means we're going to lose everything that is not the tail when the tail moves. So what used to be the tail is no longer accessible after we add an element and move the tail to point to that element. So a stack is exactly like that. If we had constant time get and remove, what does that allow us to be able to do? It ends up that it's really good at storing a history and accessing the most recent elements of a history. If we don't need to search through that history, we only need to access the last element of that history. So let's introduce a stack object from that perspective or from that mindset. So it's a new abstract data type. It is not a list anymore. A list is the only abstract data type that we've seen up until this point, but a stack is a new one, even though it's implemented with a list. It uses another abstract data type underneath the hood to store everything. But we are going to implement those restrictions that we are talking about to make a stack. So this means that for a stack, we cannot add in the middle. We have that functionality for a list, but we are going to ignore it when we implement a stack. There is no reason for us to be able to add in the middle. There is no reason for us to be able to remove from the middle. We're placing that extra restriction that the only element that we can see and manipulate is that last element that was added. In addition, we can't access any element in the middle. We can't even look at it. A visual for a stack, I like to think of a stack of plates. Imagine that you are unloading a dishwasher, and that dishwasher has a bunch of plates in it. You need a constant time way to access a plate. If you have a stack of plates in front of you, what is the only plate you can access in constant time with a single action? The top plate. If you want to access a middle plate, assuming that you cannot pick up multiple plates at the same time, you would have to remove elements from the stack of plates until the element that you wanted was on top. Then you could grab that. But now you've made a mess of the stack. But you can only ever access that top element of the stack. You can't go dig a plate out of the middle of a stack. You can't take the bottom plate off the stack. You can only interact with the top element of the stack. You can put a new plate on top of the stack, or you can access the plate that is on top of the stack, but everything else is gone. Or it's in the abyss that is the stack of plates. So I like the dishwasher example a lot because it really visually illustrates this concept very well. So you can easily put a clean plate away by putting it on the stack. You can easily access the top clean plate by removing it from the stack. So there's only one place you can put it without modifying the existing stack. Top of the stack of plates. Similarly, you're really hungry, you want to go put food on a plate, all plates are identical, so which plate requires the least work to get to? The top one. So we call the stack a LIFO structure. Because of this, we call it this stands for last in, first out. We can only access the top element. The last element that we put in the structure is the first element that we go remove from the structure when we need access to it. Which means, of course, that the stack of all of the abstract data types is the best partier. It's the life of the party. I literally can't help myself. Whenever I write slides, I have to put something ridiculous somewhere in them. It's a Monday, I don't blame you. So what underlying structure should we use for a stack? Because just making a stack by itself isn't really going to help us that much. It makes the most sense if we're going to implement a stack to use an existing structure. So we can implement a stack with an array list. Would that work? Could we do that? That means we don't have to define the functionality. All of the functionality is already defined for us. We just have to write the associated restrictions that says that when you call this particular method of a stack, we're going to convert that into the associated calls to the array list to accomplish what we want to do. We just have to make sure, because a stack is expected, that everything is constant. We need to make sure that we are only accessing the array list in a way that would be constant time. We can't ever do something that can't be constant. Could we do it with a linked list? The answer is yes, we could. Yeah. Yeah, so you can implement a stack with any kind of list. So how do we actually do that access restriction? That means that the list needs to be hidden within the stack. We cannot allow public access to this underlying list. So the list is a field of the stack object, and it needs to be private because we cannot allow access to this list. All of the methods that we write are going to allow access to the list, but only in the ways that we define. I think that learning about a stack really shows and is a great example of encapsulation. So as you've learned about encapsulation in prior classes and the importance of privacy, this is an excellent example of that. If we're going to utilize some tools with this stack, we cannot have our rogue user interacting with it in ways that they shouldn't be. So let's talk about the stack itself. What do we need to store to make this concept work? So we're going to talk about the fields. I like to think of, you break down an object into its fields and methods. I call them the state and the behavior because that's what they define. The state is just says, what are the aspects of a stack that are its physical attributes, really digital attributes. But you can think of it like an object. What are the attributes of that object? So we talked about one of them already. We're going to store as a field the underlying list that is storing the data that the stack needs to store. So the list is a field. What else do we need or would like to have for its functionality? Remember, everything that we put in here needs to have constant time or has to have a reason to be there to be accessed or manipulated in constant time. Yeah.
Most recent element added to the list.
You could think about that element. We need a way to access it that is constant. That's probably behavior, which would be good. We need some way to access and manipulate. And if it's going to be a verb, something that involves interacting with the object, then we're going to write a method for it. Great thoughts, though. We will be getting there momentarily. Any other limbs or something that if you were to take a snapshot of a stack, what would we go look at? Yeah, something like the size of it, how many elements are in it. We can't access all of those elements, but it's useful to know how many elements are in the stack. What's nice about the size as well, if we know the size, we can use the size as an index into the associated array or list. All right, now for behavior. What is it that we want to be able to do to a stack?
Pop and push, so take.
Yeah, we call them push and pop are the methods of a stack. So the first one is a push. We're going to take some data and we want to add it to the stack. Note that we do not specify a position because that is abstracted from the user's perspective. A stack, like a stack of plates, when you add a plate to the stack of plates, it doesn't matter how many plates are already in that stack. It's the same behavior. Put a plate on top of the stack of plates. Works exactly the same if there's 1 plate, 0 plates, or 800 plates on the stack. It still goes on top of the stack. Pop is our removal method. It's going to take the top element of the stack and return it. Again, there's nothing in here that tells us anything about the size of the stack, or works with an index or anything else of the sort. From the end user's perspective, it is just something you can do regardless of the size of the stack. We also want to be able to look at the top element of the stack without removing it. So we're gonna call that a peek. This is something like, is the top plate clean enough for me to eat off of? You know, it doesn't involve removing the plate from the stack. You just go look at it on the top of the stack and you say, is this good enough? And based on that answer, you could leave it there. You could pop it off and put it back in the dishwasher if it needs to be washed again. We also want to implement a size method, which is again, why we wrote the size on our linked lists. Even though we had access to a field, the fact that we can query the size means that if we implement a size in our list, then we can easily query the size of anything that uses this list as its underlying structure. There's one other element of a size that is important to be able to know without structuring the Boolean expression for it. So we're going to implement it as empty that just tells us, are there 0 elements on the stack? Yes or no. And this is usually used for something like an error checking. If you try to pop on an empty stack, then obviously we should throw some kind of exception and not attempt to do that without looking first. So let's spend a chunk of the rest of class trying to implement this. Remember that you have the underlying list. So any functionality of that list is something that you, when you're writing this stack class, have public access to. So you can manipulate this stack however you want. Don't try to reinvent the wheel. When you're writing push, there's going to be some add method of a list, because that exists. We shouldn't have to rewrite that. So the code for this is actually very simple. If you find yourself writing more than just a few lines, you're overcomplicating it. Each one of these methods should be very short. But also make sure that everything you're doing is constant time, because everything that this does needs to be constant time. So you cannot access or modify the underlying list in a way that is not constant. So let's go ahead and do that. Groups of 1, 2, probably no larger than 3. Give everyone a chance to think and contribute. 4 wouldn't be the end of the world. So let's go ahead and do this.
Yeah. And I was gonna make like 2 constructors, one that like takes a path from this. And then one. To move this.
Right, or to the very least, merge. But I also like to talk about radius counting this time. The ones that I feel like there's a use case for. Although I don't usually use heap sort, but knowing about heap sort helps to reinforce.
Yeah.
It's linked it's very briefly there. It's also talked about now. I try to. I really think we should be pushing algorithms further than we do and bringing some of that back into the structures. In a quarter system, you have 10 weeks for algorithms. And there are so many algorithms that we just want to cover, or should be covering. You don't just stop with the basic graph algorithm. You have to go into the depth of.
There's like the benefits.
Oh. Yeah.
Try to turn it. Or series of.
Yeah. Yeah.
Well, you said
Yeah, we're gonna be implementing stacks in and then I'm gonna be having people do at the very least postfix, possibly prefix, the implementation. So there's gonna be implementing the stack entity with their underlying linked list objects. And then we're going to be writing a post, at the very least a postfix solver with our stack, like quite possibly a prefix solver with our queuing.
Array list has like class.
I love that. One more with that. This one. Talking the other girl.
I go do this stuff, right, Rash? Like if I'm on the day.
Talk about trees, yeah, I'm doing the same.
What you say the array?
Yeah, last.
I'm worried about first.
They have to put in. Oh. It's much like the sound method, so.
How's the start of this process going? How do we feel about getting started? So are we feel like we have a sense of direction? That's good. Good start. Anyone struggling to get started, knowing what to do? It's okay to say yes. Give me a sense of how much structure to throw around this. Yeah.
That does make sense, like I can implement them and get started.
Yeah, so we need to implement all of these methods, and we talked about the fields on the last slide, so that basically one of those fields is going to be a list, and that means that we're gonna have all of those lists features. So how do we said that we're gonna have a restriction that we can only access the last element, the tail of the list. If we were doing a linked list, it would be the tail, but it's a little last element of an array list. So if we want to push, we need to convert the concept of pushing to a stack into what are the associated calls to a list to do that. And that's add at the end. So all push is going to be is a call to add at the end that's going to say this element that's being passed in, that's the element that we want to add to the list. So I would start possibly with the constructor. The constructor's job is to convert the concept of an empty stack. What does a list need to be to represent an empty stack? And it's a list of no elements. So just make sure that you're calling your list constructor inside of the stacks constructor, setting the value of any of the other fields. So we said there's a size, make sure we set the size to 0 initially.
You don't have to put.
And you're starting to think about pushing. You're gonna take that element, call out at the end for the list.
Well.
And now we need to manipulate the size of the stack, because that add at the end is gonna change the size of the underlying list structure, but it's not gonna change anything about the size of this stack. We're gonna use an array list for this one. Yeah, so you can just use the built-in array list, and then part of your next homework will be to implement this for your linked list objects.
You can still
Do we have to store variable called size, if we can just access it?
The array list size, it's useful because if there's any, it allows us to make it publicly accessible to the user. And I guess you could implement size as just the not having this size, but then clearing the array list
We just have to
size.
update it every day.
Yes.
Call it list on size anyways.
Right. So you can do that. It does create one small potential bug where if if you introduced a bug to your program where the size of the underlying list and the size of the stack were not to be the same, it might make it a little bit harder to identify or to test whether that is correct.
Probably every day.
Yeah, or if there's any other concept in it, but it's an extra point of failure. Or an extra point of failure that's.
Why would you? Your actual.
Yeah, it's really up to the implementer. I agree that it is unnecessary.
I am excited.
Not really.
Yeah.
Yeah, they're very simple structures, which is great.
Yeah, I just, so I make like mobile.
Yeah, you need one of these in order to solve towers of annoyance. That's why I like doing this right after the noise, and then it allows you to see, this is the description, structure that we, this is all.
Oh, yeah.
Yeah.
I don't want people to implement it. The pain in the ass. Just see the recursive one. Yeah, I'd rather do this.
Yeah.
Yeah, usually it's a week or two to get turned around on that. Once it's done, I will certainly be looking at the stats as well, since I have Tony send me all of the stats on a student by student breakdown, so I can look at it and see. That's another way that I look at and check, is my intuition about what this person knows, is that correlating to the score that they get, and that becomes an important metric that I have for evaluating aid.
Tony's the guy who probably.
Yeah. Yeah, he's the other data structures, he's the usual data structures professor. And then he administers the very. I think it's in the, so you signed up for a Canvas course? As part of taking that?
2 weeks to grade.
Yeah. Yeah, if you enroll in that Canvas course, the single grade that gets posted for that course is your AIM score.
I'm excited to see that.
Oh, no, see, right there, boss. I was. Oh, yeah. Yes. Put the thing. We don't have a.
After the end.
She wouldn't eat no, but I have the author's note and.
Well.
So it's like.
You just return. Stuff removed last.
It's like.
Oh, that vaccine, yeah. No, that makes sense, because removal is slow. Because it still calls it when you return it.
Yeah, it does. Okay, thank you. Oh, that's good. I was wondering about. Wait, so I don't think we did part of the. Yeah, that works.
That being said, though, if you alter the size, we like.
Oh.
Still throw it. It's very good class, like. I'm assuming whatever.
Yeah, so I think.
Yeah, no.
240 and math. I literally like said that in our class and I was like, no, screw this.
Well, this remove last attached to it, right, so I think it was fine.
I sent her an email after and like I have a doctor's note.
Yeah, with 240 is.
Oh, no. You. Oh.
I'm just cross.
I was ready to go to say, look, I tried. This, like, I couldn't go to all this.
Yeah.
Simple.
I think the whole thing is done and I don't think she wants students to succeed.
And then I had to do. I wouldn't ask moral judgment on that. It is still.
All right, I have our fields and I have a constructor written up here in case that is useful to you. What if you really guess? How do we write push for those of you who have written a successful push? Yeah.
Use the add last method,
Yeah.
in the element, and then increment the size by 1.
Yeah, we just say elements dot add the element. That adds at the end. And then bump up the size. That is the entirety of push. It's done.
Can't go back.
Just not add.
Yes. Yeah, add is overloaded just like ours was. There are two different add methods. If you pass it just the element, then it adds at the end. If you pass it an element and an index, then it adds it at that index.
There's also like an add last method. What's the difference? I wonder if they're being used on stage.
I'd have to look at the documentation. I'm sure there's a complexity reason or there's something with regards to what it's meant for that.
But it wouldn't matter which one we use.
Yeah, I don't believe so. Question?
Add to here, size plus plus.
It would for the lists, but we're keeping track of, for some reason, and we can have a discussion about the extent to which this is useful. We're keeping track of a separate size of the list and a size of the stack. Even though they should always be the same, yeah, this size is this stack's size.
Is there any reason that the listing use the tail as the top of the stack versus like the head?
For an array list, it's extremely important, because if you're adding and removing at the head, then every single time you need to make space for it. And, or, yeah, decrement the size, so that would turn both push and pop into linear time operations. And that cannot be allowed. Yeah. All right, we'll write another easy one.
Interesting.
Would it matter?
That's a great question. Now, that's a very important homework question.
Would we care whether or not we're pushing a null? It's like if the element is key, do we care?
Yeah, it depends on the implementation of the stack. We may want to throw some kind of exception if that's done to allow that, but what's nice about pop is it returns something of type T, so it could return a null. So by not allowing it, Right, this is why allowing it, we allow null to be one of those values in case that is a legal use of this. But then we put the onus on the user to know that if they're going to do that, then that is something they have to consider and account for. So we can't dereference the null without their own code breaking.
I do not.
Pop is a little bit harder. When we pop, we do need to check for something, so this will throw an exception. I'm gonna call it an illegal state exception, which we need to know. Eventually, this will tell me that I need to import it, but the reason we want to throw this is if we attempt to pop from an empty stack. Regardless of whether there's some nulls in there, it's okay potentially to allow null to be pushed to the stack or to pop null from the stack. But we cannot pop from an empty stack. There should be a difference between returning null, saying null was on top of the stack, and I was not able to pop from the stack. So this will just be, how would we determine if this illegal state exception should be thrown? Well, we should just call is empty. If the stack is empty, then we should throw the exception. We can add a message. How are we gonna pop after this? How do we do that? Yeah,
We just do list out remove.
we want to remove from the list, potentially. If we remove from the list, does it store the element that it removes?
Is remove not return,
It does return the element, so we can
Yeah.
say something like
pages do return.
that element is. Where do we wanna, what index do we wanna remove from? Size -1? Yes, that is the right answer, because the index size -1 is going to be where the last element is stored. Yeah,
Use remove last.
if you use remove last, yeah, you could do that too.
Could you not just put the element dot remove size -1 into the return call? Wouldn't that do the exact?
Just do that. Well, we would want to make sure that we decrement size first.
Yeah,
So if we did the size decrement before we did this, then yes. If we want the remove to be sure that it works, because what other kinds of exceptions could we throw from remove?
or illegal argument exception.
Yeah, so we could go directly from this, but I want to allow the remove to do something that might fail. So rather than make the code slightly shorter, that's probably not a huge deal. We just do this and then return the element. And now if our code breaks here, then that's fine. All right, all that's left for us to do with our 1 minute is to do peak in size. I think we can quickly do that. Gonna look very similar to the start of pop. So luckily peak, we're not trying to remove it, so we don't need to check for peaking on an empty stack. That's just going to be a check, because we want to make sure if it is empty, then we still want to return something. So here we're going to return null. If you get null back from Pete, that says there was nothing on top of the stack. And then we can just return. Now we can use dot get rather than dot remove, because we're not trying to do that. We just want to remove or to get at index size -1. And then the very last thing, and we'll come back and test this tomorrow, is to implement a getter for our size. And that's the entire stack. It's literally all the code for the stack. So it is a very simple structure that makes significant use of the underlying list. And in using its functionality. But note that by interfacing with this stack, there's literally no way we can do any of this in that takes more than constant time. We have successfully restricted this to be a constant time only structure. Yeah, we'll come back tomorrow. Take a look at it. 2 lines.
Write it.
I thought so, but
Yes, there we go. This allowed bill is being used.
It's like, I'm just gonna basically like, if it's empty, they say, we should do the top, and I swap.
And it would be very easy to just push. Throw that.
Every Cascades failed, I was like, what? It's always, it doesn't try to check.
Being built is what an extra exception.
It's got data.
Either one of those would be.
Like, I'm checking. Why are you? It said, it said, this should have been.